All right. All right, so feel free to stop me at any time if you have any questions. I'm going to go through the key concepts that are going to be on the test. And the first one that let's go through right here is graphing exponential functions. And log functions. And the reason why I do this right here, because it's actually best to do them together. So let's say I have the function for the graph, for example. Graph the function, let's go y is equals to 3 to the x power. The simplest way to graph these functions right here is to make a table of values. So you have your x, and you have your y's. And so you might plug in, say, -2, -1, 0, 1, and 2 into the function to get the coordinates. I like to start at the bottom. So if I plug in 2 right here, this is going to be 3 squared, and 3 squared is 9. So that's going to be 9. If you plug in 1, that's going to be 3 to the 1, that's 3. You plug in 0, 3 to the 0, that's 1. So far, so good. Now, when it comes to the negative numbers, right here, plug in -1, that's going to be 3 to the -1. What we have to remember is that the minus sign means to take the reciprocal. And the reciprocal of 3 is actually 1/3. So this actually means 1/3 to the 1 power, which of course is just 1/3. Again, to go from here to here, the only thing I'm changing is the minus sign. That's the only thing that I'm changing right there, is that minus sign. That minus sign simply goes away. That minus sign simply goes away. And so you have that radical. Plugging in the last one, -2. So that's going to be 3 to the -2. Again, the minus sign simply means take a reciprocal. So this is actually 1/3 squared. And 1/3 squared is simply 1/3 times 1/3. That's going to be 1/9. And so this point right here is going to be 1/9. Questions there? Now there's some things to note. The base for this function is 3. If I know the base right here, you can see there's a simple pattern. 1/9 multiplied by 3 is 1/3. 1/3 multiplied by 3 is 1. 1 multiplied by 3 is 3. And 3 multiplied by 3 is 9. And so what we see right here is every time the x value increases by 1, you need to multiply by 3. And that is how you get the points to graph the function. And so the nice thing here is that once you find one point, you find all the points by simply using that same number and over and over. Obviously, you could always do it backwards and just divide by 3 each time. And you could work backwards if you prefer. 9 divided by 3 is 3. 3 divided by 3 is 1. 1 divided by 3 is a third, and so forth and so on. Any questions there? The other point to note is that the minus sign means a reciprocal. So remember that all of these x's right here are exponents. And so because they're exponents, 2 right here is attached to the number 9. Look at -2 is attached to the reciprocal 1/9. And so again, using that principle right here is that once you do half of the numbers, you automatically have the other half as well. Questions there? And so that's a little bit in terms of setting up and these things right here. Now to graph the function would simply be to plot the points. So at -2, the graph is 1/9. At -1, the graph is 1/3. At 0, the graph is 1. At 1, the graph is 3. 3. And at 2, the graph is 9. So it's going to be way up here. And so you see this graph that looks like this. This graph right here has a horizontal asymptote. And HA of y is equals to 0. Questions there? Now, a point of emphasis is not only be able to graph this function right here, but graph its cousin. So let's say I wanted to graph the function f of x is equals to 1/2 raised to the x power. Again, the reason why these graphs are cousin is because this right here is just a reciprocal of a whole number. And so because of that, a lot of the patterns we see will still hold when we try to graph the function x, comma y, -2, -1, 0, 1, and 2. Again, I like to start at the bottom. That just makes my life easy. Plug in 2 right here. So that's going to be 1/2 squared. That's going to be 1/2 times 1/2, which is going to be 1/4. So this point right here is going to be 1/4. This automatically means that this point right here is going to be 4. Because minus sign means take the reciprocal. I can verify that 1/2 raised to the -2 is going to be, take the reciprocal of 2, that's going to be 2 squared. Again, the minus sign right here means reciprocal. Reciprocal of 1/2 is 2, and of course 2 squared is 4, which of course is the answer I'm looking for. Questions? I thought somebody had a question. All right, not hearing no questions. All right, that's cool. That's cool. That's cool. Again, like you're saying, the principle, the base is 1/2. And so what happens is I'm multiplying by 1/2 to go from term to term. And so if I wanted to, I can literally just list all the terms by just going 4 times 1/2 is 2. 2 times 1/2 is 1. 1 times 1/2 is 1/2. And just like that, I have found all the values, all the table of values, just like that. Of course, you could plug in every number one at a time. You get the same answer. But again, my point being, again, look at these right here. They're reciprocals of each other. There are lots of patterns hidden within the table of values for graphs of exponentials. And once you start seeing those patterns, then the graphs aren't that bad. If I would graph the function at -2, the answer is 4. At -1, the answer is 2. At 0, the answer is 1. At 1, the answer is 1/2. And then at 2, the answer is 1/4. And so the graph function looks like this. Again, having the same horizontal. Again, having the same horizontal asymptote, that is y equals 0. H A y equals 0. Questions there? Comments? Queries? Concerns? For both of these graphs, the domain is going to be all real numbers. The range are only going to be positive numbers, right? Because the horizontal asymptote is preventing the graph from going into negative territory. And so it's just going to be all positive numbers. They all have the same y-intercept. That is a 0, 1, because any number raised to the 0 power is 1. And The only difference between the two graphs right here is that this one right here is decreasing, while this graph over here is increasing. If you think for a second, that should make sense. In this graph right here, I'm multiplying by 3. If I'm multiplying by 3, that means I'm getting larger every time. While in this graph right here, I'm multiplying by 1/2. If I'm multiplying by 1/2, I'm getting smaller every time. And so this graph is going to be a decreasing graph, while this graph is going to be the increasing graph, while this graph is going to be the decreasing graph. Questions there? So on the on your web assignment, you'll be asked to make a table of values. You'll be asked to identify the graph of the function. You'll be asked to identify your domain, your range, your y-intercept, horizontal asymptote, all that good stuff. Questions there? Now, when push comes to shove, if you have a graph and you're trying to think, you just need to line up the table of values, right? Just create a table of values. And of course, that will always take you to the right graph. Now, the cousin of your exponential functions is your log functions. Remember that logs and exponentials are inverse functions. And so what that means is that they're simply a replacing of the x and y functions. And so what happens is we take advantage of that when we're trying to graph logarithms. Graphing exponential functions is really easy. Graphing logarithmic functions is also really easy if you remember this one fact. So again, let's do 2 quick examples. If I have f of x is equals to, for example, log base 3 of x, right? What I do is I just write this as y is equals to log base 3 of x, and then I convert this to exponential form. So that's going to mean then that 3 raised to the y power is equals to x. Remember this right here? Log functions, switching to exponential functions. And so what I'm going to do here is I'm going to make a table of values for 3 to the 3 raised to a power, and then I'm just going to simply switch the x and y values. And that will give me my table of values for this graph. So x, comma, y. I think we actually did this table a second ago. -2, -1, 0, 1, and 2. That's going to be 9, 3, 1, 1/3, and 1/9. Because the two functions are inverses, I simply have to reverse the table of values to get the table of values for your log 3. So x, comma, y, 1/9, comma, -2, 1/3, comma, -1, 1, comma, 0, 3, comma, 1, and 2, comma, 9. And there you have it. You have your table of values for your log function. Questions there? And again, you can double check this. For example, let's plug 2 into the log function. Oh, wait a minute, I didn't flip the last one. I was about to say, what am I plugging into? It's 9, 2. So for the last one, let's plug in 9. And so if I have y equals log base 3 of 9, well, what power must I raise 3 to get 9? 3 squared equals 9. And so therefore, when the answer is going to be, when you plug in 9, the answer is going to be 2. And with that, that will allow me to graph my log function. And so I'm plotting points. So at 1/9, the graph is -2. At 1/3, the graph is -1. At 1, the graph is 0. Third. At 3, so 1, 2, 3, way over here. The graph is 1, and then 9 is way over here. I can't get 9 on here. And so the graph of the function will look like this. Beautiful graph, beautiful. Questions there? And basically, what's going to happen is that all of these right here are simply going to flip. And so your domain is now going to be the previous range. So the domain is going to be 0 to infinity. The domain for logarithms, only positive numbers. The range, however, is going to be all real numbers. Someone's saying hello. The y-intercept will become now the x-intercept. And that's going to be 1, 0. Again, notice that the points have been flipped, right, to go from y-intercept to x-intercept. And you can see clearly here, this right here is your y-intercept. When I switch over to the log, I now have the x-intercept. Right? Now, the graph does not have a horizontal asymptote. What it will now have is a vertical asymptote. Going up right here, you have a vertical asymptote. That's going to be x equals 0. And this graph right here is going to be increasing. Questions there? All right. Do recall your basic transformations. If I have f of x is equals to negative, for example, log base 3 of x, this is simply a reflection in the x-axis. If it's equals to log base 3 of x minus 4, that's a shift to the right. Four units. If it's on the outside, the log base 3 of x minus 2, that's a shift down. 2 units. Any questions there? All right, cool. All right, and so we now have to understand the link between logs and exponentials, and we need to be able to switch between the two sides. So if you have so converting between logs and exponentials. And so the simple rule right here is that if you have a logarithm, say I have log base 5 of 25 is equals to 2. You have to remember that this number right here is the exponent. And this number right here is the base. And so if I convert this to exponential form, then it's going to be 5 squared equals 25. If you convert the logarithm properly, the terms you get, if they're all numbers, should make sense. If you convert it properly, the terms you get should make sense. Okay, a different way to convert them, but still get you to the same place, log 25 equals 2, is you simply will drop the log and then slide the base over. You'll simply drop the log and slide the base over. And so therefore, it's going to be 25 is equal to, the base is going to be on the other side, 5 squared. And so that's how you convert from log to exponential form. Now going the other way, if I have an exponential form, for example, if I have then that 5 to the third power is 125, and I want to convert this to a logarithm, right? Again, you have to remember that this is the base, and this is the exponent. They end up on opposite sides when I convert to log form. So I write the keyword log, I put in the base, and this is going to be equal to 3, because the exponent is on the other side of the logarithm. So 125 log base 5 of 125 is 3. Okay. What power must I raise 5 to get 125? That's what the question of log is asking. To get this number right here, what power must I raise 5 to? In this case right here, that power is 3. Let's do one more example, I guess. 4 to the negative third power is equal to 1 over 64. Convert that to logarithmic form. Again, you write the keyword log, the base. Again, this is going to be equal to negative 3 because that's the exponent. And what comes inside the log is the number. I have to raise 4 to the 1 over 64 power to get an answer of 3. Questions there? Sometimes they give you the log without the answer, and they ask you to find the answer to this logarithm. So sometimes they give you the log without the answer, and they ask you to find the answer to the logarithm. So for example, they may have log base 3 of 81, and then equals, and you got to figure out what the answer is going to be. Well, what you do is you simply write this as log base 3 of 81 is equal to x. You make it into an equation, and then you convert the equation to exponential form. Drop the log, slide the base over. 3 to the x is equal to 81. You make the bases the same. So 81 is 9 times 9. So 81 is 3 to the 4th power. And so it's going to be 3 to the x is equals to 3 to the 4th power. Again, making the bases the same. And then you simply cancel the similar bases. And therefore, x is equals to 4. Questions there? Another example. Let's say I have log base 2 of 1 over 64 right here is equals to x. And I'm trying to figure out the value of x. Again, I convert this to exponential form. So 2 to the x is equal to 1 over 64. Now, 64 is a fraction, just like we saw earlier on. That simply means a negative power. The minus sign means a reciprocal. And I got to take 64 and break it down. 64 is 8 times 8. 8 is 4 times 2. 8 is 4 times 2. That's 1, 2, 3, 4, 5, 6. So that's 2 to the 6th power. And so my question becomes 2 to the x is equals to 2 to the 6th power raised to the negative 1. So in other words, I'm replacing the 64 with an equal value, but with the same base that I am looking for. Now, once I have that, I can simply write this as 2 to the x is equals to 2 to the negative 6. Again, you just need to multiply this together. And of course, then these will cancel. And so x is equals to negative 6. And that would be my solution to my problem. Questions there? I'm hearing very few questions. You guys are so quiet. Are you guys okay? Let's try some exponential equations. So let's say I have 7 raised to the x plus 1 is equals to 49 raised to the 2x plus 3. And I am trying to solve for x right here. Again, the bases are not the same, but I know 49 is going to be 7 squared. There's going to be 7 to the x plus 1 is equals to 7 squared raised to the 2x plus 3. Again, what I'm endeavoring to do is to get the bases to be the same. And that's going to be 7 raised to the x plus 1. It's going to be 7 multiplied by 2. 4x plus 6. Remember, when you have a power to a power, you multiply. And now I can cancel out the bases. So this will cancel, and then this will cancel, and that will leave me with x plus 1 is equals to 4x plus 6. Subtract 6. X minus 5 is equals to 4x. Subtract x. Negative 5 is equals to 3x. Divide by 3. X is equal to negative 5/3. Excuse me. And there you have it. You have an answer right here. Again, the key thing right here is you have to break that 49 down into two things that are being multiplied together. Questions there, kind folks? All right. I guess we can do one more. Let's try this one. Let's say I have log base 36 of the square root of 6, and I'm trying to evaluate this logarithm. Again, what I do is I simply set the equal to x, simply saying I don't know what the answer is, and then I convert this to exponential form. So 36 to the x power is equals to the square root of 6. Now, 36 is 6 times 6, that's going to be 6 squared. Okay, notice in this special case, I'm not breaking down to 3 and 2 because I need to get the bases the same. And so I'm just going to use the 6. So that's going to be 6 squared to the x is going to be, and you have to remember that a radical, it means that you have a fractional power. Square root of 6 is 6 to the 1/2 power. The 4th root of 6 to the 5th power is 6 to the 5/4 power, right? The power becomes the numerator. The root becomes the denominator. And you just have to remember that for a regular radical, the numbers are invisible. The 1 right here, and square root, that 2 is invisible. All right, so take a note right here. Again, any questions? First time I'm mentioning fractional power, how to convert from a radical to a fraction. And then again, you multiply these together. That's 6 to the 2x is equals to 6 to the 1/2. And now my bases are the same, so I can cancel out the bases. So 2x is equals to a 1/2. And of course, the last step is to then divide by 2, or because of the fraction over here, multiply by 1/2. These will cancel. X is going to be equal to 1/4. Questions there? Comment. Queries. Concerns.
Could you move, sorry, could you move the screen over to the right a bit so I can see the 4 square root of 6 to the power of,
Can you
over
see
to the right? Oh, wait, scroll down a bit more. Okay, there we go.
Oh
I
yeah,
see it now.
you just hit the there's a little minus button. Is the picture covering it up? Hit the minus button and the picture should
Oh,
go away.
thank you. Thank you.
So you can see the whole screen. All right. Anybody else? Questions? All right, cool. Now, again, staying the same theme, there are some times when you have an exponential function, but you cannot get the basis the same. Again, the same vein of solving equations. For example, excuse me, let's say I have 7 raised to the 5x plus 2 is equals to 12. 12, is 4 times 3, which is 2 times 2. Again, and 7 is prime. So there's no way I can get the basis to be the same. And whenever you come up in that situation, what you have to do is you have to cancel out one of the bases. And the way you do that is by taking the appropriate log on both sides. Since I want to cancel out 7, what I'm going to do is I'm going to take a log base 7 on both sides of the equation. So I have introduced log base 7 on both sides. And the reason why I do that is because this will all cancel out, because log of 7 cancels out because they are inverse functions. And so this leaves me with 5x plus 2 is equals to log base 7 of 12. And then from here, algebra tells me there are 2 steps to go. I simply need to subtract 2 and then divide by 5, right? Subtract 2 on both sides and then divide by 5, right? And so then that tells me then that x is going to be log base 7 of 12. I have to subtract 2, and then I have to divide by 5. And that will be the solution to my equation. Questions there? Comments? Queries? Concerns? All right. And then the last one right here, your log equations. Let's say I have ln of x minus 5 over 2 plus ln of 10 is equals to 2 times ln of x. And I am here trying to solve for x. What we have to do is we have to simplify both sides so I have a single log on each side. And so what that means right here is that we have to remember that the plus sign right here means to multiply. So that's going to be ln of 10 times x minus 5 over 2. And again, the power rule that says that the x comes to the top, so it's going to be ln of x squared. Plus means to multiply. And then the 2 right here becomes the power. Now that I have done this simplification, I can strike the logs on both sides. I can cancel log on both sides. And so that leaves me with 10x minus 5/2 is equals to x squared. I gotta be very careful. Distribute the 10. That's going to be 10x minus 50 over 2 equals x squared. So that's going to be 10x minus 50. No, 25. How do I get 10 in my head? Equals x squared. I'm going to take everything over. That's going to be x squared is equal to negative 10x. Oh. I'm not doing this one. Must be sleeping. That's going to be x squared minus 10x plus 25 equals 0. When I move everything over, nothing gets left over here. And then I need to factor this thing right here. I need two numbers. When I multiply them, I get 25. When I add them, I get negative 10. Those numbers are negative 5 and negative 5. And so this factors into x minus 5 times x minus 5 equals 0. And so I go x minus 5 equals 0. So x equals 5. Now, the only thing that you have to remember is that you have to check this answer. Okay? The thing about logarithms, because remember, see, this is a log equation. Thing about logarithms is that you go all the way back up to our good friends right here. The domain for logarithms are only positive numbers. And so I have to check to see if I have to take the log of a negative number. If that happens, then my answer, then the question would have no solution. I have to strike my answer. So I have to check it by plugging it back into the original equation. You have to use the original equation. Plus ln of 10 equals to ln of 5. Plugging back in. Now 5 minus 5 halves, that's going to be a positive 2.5. That's going to be ln of 2.5 plus ln 10 equals 2 times ln 5. And what you'd note is that none of these numbers are negative. All positive. You cannot take the log of a negative number, but that doesn't happen here. And so that means that this answer is fine. Again, for argument's sake, just so I can prove the point right here, is that let's say the question was ln of, say, x minus 10, and I got an answer of 5. I plug in ln of 5 minus 10, that gives me an answer of ln of negative 5. This does not make sense. And so then that would mean that x cannot equal 5 in this example. Okay? And so in this case right here, the problem would be, the answer would be no solution. All right? And so you have to keep that in mind. Excuse me. You have to keep that in mind when you're working with your logarithmic equations in particular, is that you have to check your answers, because you cannot, again, you cannot take the log of a negative number. Questions there? All right, and so that takes us to the last section, I believe. Yeah, and our last section right here are your properties of logarithms, your laws of logarithms. So you have the log laws. You have the sum log, the sum property. It says if I have two things that are being multiplied together, so x multiplied by y, then this is going to be log x plus log y. So for example, if I have log of 3x, this is going to be log of 3 plus log of x. This also works in reverse. If I have log base 2 of 5 plus log base 2 of x plus log base 2 of y, the pluses will become multiplication. And so it becomes log base 2 of 5 times x times y. Questions there? I normally memorize it one way and then just know that the other way is just reversing the property. Another example, if I have a log of, say, x plus 1 multiplied by, say, log base 5, x plus 1 times, say, y minus 3, it's going to be log base 5 of x plus 1 plus log base 5 of y minus 3. Again, I cannot split these because that's not multiplication. You can only split multiplication. You cannot split addition or subtraction. And so this is as far as it goes. Questions there? The difference property is exactly the sum property, but in reverse. So if I have log of any base of x divided by y, then this is going to be log of x minus log of y, where anything that's in the denominator of the log splits out to become a negative log. Okay. And so that right here is your difference property of logarithms. The nice thing about the difference property is that it works lovely even for complicated logs. So if I have log a times b divided by c times d times e, this is going to expand to log a plus log b minus log c minus log d minus log e. Any term in the numerator becomes a positive log. Any term in the denominator becomes a negative log. And if you just remember that fact, you can expand and contract logs very quickly. Questions there? That right here is the most important property when it comes to expanding or contracting logarithms. And so, again, let's do it in reverse. If I have log of x minus log of y plus log of a, this was going to be log of xa over y. The negative log ends up in the denominator. Questions there? All right. And there's one last property. So you have your sum property, you have your difference property, and the last one is going to be the power property. The power property is just a shortcut of the sum property. This power property says that if I have log base a of x raised to a power, I can put that power out front. I can say I'm just multiplying by that value right here. Okay. Like I was saying, this right here follows, let's say I have log base 3 of 5 to the 4th power. Well, let me show you how the 4 gets in front. So log base 3 of 5 to the 4th power is really log base 3 of 5 times 5 times 5 times 5, right? The 4th power means multiply by yourself 4 times. And so this is going to be log base 3 of 5 plus log base 3 of 5 plus log base 3 of 5 plus log base 3 of 5, right? They're going to be 1, 2, 3, 4 logarithms, all log base 3 of 5. The multiplication becomes addition. Yes, but there are 4 of them. And so this is simply going to be 4 times log base 3 of 5. The power property simply says, skip all of these steps. We know what's going to happen. Just put the 4 in front. 4 log base 3 of 5, and save yourself, time and money. That's all the log property simply says. Save yourself some time and money, and put that number in front. So when you have an example, log base 2 of, say, s to the 3rd power divided by 5 times t squared, positive, negative, this is going to be log base 2 of s to the 3rd minus log base 2 of 5 minus log base 2 of t squared. Again, following our basic rules from up here, or if you are in the numerator, you're positive. If you're in the denominator, you're negative. But now I need to just move the powers out front. So that's going to be 3. I get 3 out front. Nothing for this one, and then a 2 out front. Yes, I should have done step 1. It's going to be log base 2 of s. The 3 has been moved in front. Minus log base 2 of 5. And again, the 2 out front. So minus 2 log base 2 of t. And that's us expanding the logarithm. This also works in reverse. If I have, for example, 1/2 log base 7 of x minus 2 times log base 7 of 5 plus 4 times log base 7 of x plus 1. Again, I have 2 of them that are positive. That's going to be log base 7 of x to the 1/2 power. Remember, the 1/2 comes up here. Multiplied by x plus 1 to the 4th power. And then I have this one that's negative. That goes to the denominator. And so it's going to be 5 squared. And then the only thing I'll remind you is that the 1/2 power simply means a fraction. And so then this is going to be log base 7 of the square root of x times x plus 1 to the 4th divided by 25. And I have now contracted and compressed the log together. Questions there? Comments? Queries? Concerns? All right. So that's what I have for you guys today. No one has any questions? I'm going to stop the recording now then.